All right, in today's lesson, we're doing section 7.2, and it is on inverse relations and functions. So inverse relations and functions. So we've seen the word inverse, and we've used it in a lot of different ways. The additive inverse of 3 is negative 3, meaning what can I add to 3 to cancel it out? And so 3 plus a negative 3 is 0. So when we're adding, subtracting to cancel, we want to zero it out. The multiplicative inverse of 5, what can I multiply by 5 to cancel it out? A lot of people want to say it's 0, but it's actually 1/5. When we multiply and divide to cancel out, we're trying to get to 1. So 5 times 1/5 is 1. We use inverse operations all the time to solve equations. We can also find and apply inverse to relations and functions. So to graph the inverse relation, you can reflect each point across the line y equals x. Now I want to remind you real quickly about the line y equals x from all the work we've done on our linear graphs. A lot of people get stuck and don't know how to graph it. Can't I just put a 1 in front of this and add 0? Now that looks more like our slope-intercept form. So I'm going to go ahead and just show you real quickly on an xy axis where this line lays. And I want to remind you that this is not a line that we're actually graphing, it's our line of reflection, okay? But when we look at this, if y is equal to x, I can really just graph that by saying if x is 1, y is 1. If x is 2, y is 2. 3, 3, 4, 4, etc. I can also look at that and say I start at 0, I go up 1 over 1, up 1 over 1. And I'm going to put this in as a dashed line because it's truly not a line that's showing on my graph as we do these. It is a line of reflection. So these are going to reflect over y equals x. All right. The equivalent of doing this is switching the x and y values. So if I have a point over here at 3, 1, that point at 3, 1, to find its inverse, I am actually just switching the ordered pair to 1, 3. And if I would take this ink blot and I would fold my paper on my reflection line, it would fold up here. So 3, 1 is inverse becomes 1, 3. And that's it. We are switching the x and the y values of each ordered pair in a relation. All right, so a couple reminders from earlier studies. We know that a relation is a set of ordered pairs. In general, every x has a y. Every x has a y. So everybody has a buddy, everybody has someone to pair up with. A function is more specific. It's a relation in which each x value has at most one y value. Our way of saying it was every x has exactly one y. Every x has exactly one y. Now that's if we're looking at ordered pairs. If we're looking at a graph, we can do the vertical line test. And so again, these were all things we have done. The vertical line test is actually taking a vertical line and drawing them down through your graph. A vertical line can hit no more than 1 point. If a vertical line hits more than 1 point, that means you have more y values for that x. So that goes back to that x would have more than one y value. So vertical line test. Any vertical line can hit no more than 1 point. No more than 1 point on the graph. All right, so we're going to get into looking at this by graphing. So the first thing we're going to do is we're going to graph the relation and we're going to connect the points, and that's important. If we're not connecting the points, then this is considered a discrete graph and we have 5 points, and that's it. But since we're connecting the points starting at 0 going to 8, it's going to be continuous between those. So go ahead and just take a second and let's graph these points. So we go to 0, 2, so 0, 2, plot a point, 1, 4. You're going to notice that this is not linear. and it jumps to 8, 7. Now, since the directions told me to connect the points, I'm going to start at my first point and I'm going to connect to my last point. Notice I have no arrows here. So it starts here and it connects and it stops there. All right, the next thing it asks us to do is to graph its inverse. So in order to find the inverse of a function, it is simply switching x and y. That's all I'm going to do. So I'm going to make a new t-chart, x and y, and 0, 2 becomes 2, 0, and 1, 4 becomes 4, 1. 2, 5 becomes 5, 2. Switching the x and y, 4, 6 becomes 6, 4, and 8, 7 becomes 7, 8. I think it's worth a double check to make sure you really did flip them and you didn't just rewrite something. And then go ahead and graph these ordered pairs and again connect the points. So I'm going to start at 2, 0. So we can see that reflection idea. Go to 4, 1, 5, 2, 6, 4, and that last jump is 7, 8. And again, I'm going to connect my first point to my last point. And that is what the inverse looks like. Now I want to give you a reminder here of that line y equals x. So the reflection line, so it reflects over y equals x. So I'm going to go ahead and sketch that line. 1, 1, 2, 2, 3, 3. Start at 0, go up 1 over 1. And so I'm just going to sketch that line in as a dashed line to show it's a line of reflection. So it's not part of my graph, but it's showing where they reflect. So if you would take your paper and you would fold it right along this line, this point here at 6, 4 would reflect back over to the original point of 4, 6. This point on my inverse of 7, 8 would reflect back to the original point of 8, 7. And notice if the lines intersect, they intersect on the line y equals x. So that's what it looks like. Now let's talk about our domain and range. Domain is what the x values can be, and range is what the y values can be. So in my original function, the domain, if we did not connect the points, would be 0, 1, 2, 4, 8. If we did not connect the points and it was discrete. But since the directions told you to connect the points, it actually starts at 0. If we scan the x-axis, my domain starts at 0, and the last place my red line stops is right here at 8. So in interval notation for the domain, in interval notation, it would be 0 with a bracket to 8, because both the 0 and 8 are included. I can pick anything in between. If I go to 1.5, there's a point on the line. If I go to 2.9, there's a point on the line. Okay. If I want to do this in set builder notation, we have our bracket x bar x such that 0 is less than or equal to x, which is less than or equal to 8 with a bracket. All right, the range of our function is the y value. And so again, if we were doing a discrete graph and we did not connect the points, the range would be 2, 4, 5, 6, 7, and that's it. We would just list them in roster notation with commas. But because we connected them in the directions, that means that we start, my red graph starts here at 2, and it goes up and it ends at 7. So you want to scan your axis. So the low is 2 and the high is 7. Now the range is talking about the y value, so in set builder, it's y such that 2 is less than y, which is less than or equal to 7. All right, try that again. 2 is less than or equal to y, which is less than or equal to 7. And that would be interval notation, set builder notation. Now, if I'm talking about the inverse, finding the domain and range of the inverse, well, you need to think about this. Didn't I switch the x's and y's? So my y's are now my new x's. So that means if I come across here and I look for my domain, the first x value I hit is 7 or 2, and the last x value I hit is at 7. So my domain goes from 2 to 7. And so if you look, your domain came from the old range. Then if you look at this, and I want to talk about the range of my new function, I would start at 0 and I go up and I stop at 8. And that is exactly the domain of my original function. All right, we're going to go into talking about inverses with functions now. So we're going to talk about the notation here. So when the relation is also a function, you can write the inverse of the function. So function notation is f of x. F to the negative 1 of x stands for the inverse function. So f to the negative 1 of x really means the inverse of f of x. Now remember, f of x is the same as your y value. F of x is the y value, it's function notation. So any problem that you're given in function notation, you want to give the answer back in function notation. So we see f of x, it's not f times x, it's the function of x. We see a power of negative 1. That's not really a power of negative 1. It doesn't mean the reciprocal. We're referring to this rule. A to the negative n is equal to 1 over a to the power of n. Something we've talked about this year, something we just did. When you see a negative power, it normally means take the reciprocal. But in function notation, it's just saying the inverse of the function. So this f is not a variable, it's just notation for the inverse of a function. So you can see right here, I have a function f of x, and it's x plus 6. The inverse function is x minus 6. So here's the original, here's the inverse. So functions that undo each other are called inverse functions. And so what this is quickly showing you is if I have an input of 3 and I put it into my original function, everywhere I see an x, I'm going to put a 3. So I'm going to f of 3, 3 plus 6, I get f of 3 is 9. Now take that answer and put it in the inverse. So everywhere I see an x, I'm going to put a 9. And 9 minus 6 is 3. So the inverse function of that was 3. And so what they're trying to show you is if I put in 3 to the function and I turn around and I spin it through the inverse function, I get it out. So the function and the inverse function cancel themselves out, and I'm right back to where I started. So a function and its inverse cancel each other out. And we'll be revisiting this later with compositions. All right, to find the inverse function, use inverse operations. This is something we've always done. When we solve an equation for x or for y, we are always using inverse operations. How do I get rid of addition? I subtract. How do I get rid of division? I multiply. So in the example above, they're saying 6 is added in f of x, so 6 is subtracted from f to the negative 1 of x. Now we have some examples here about writing inverse functions by using inverse operations. So they want you to look at this and see the inverse operation. If I have f of x equals 2x, the inverse of multiplication is division. So the variable x is multiplied by 2, so its inverse is to divide by 2. So it is as simple as doing f to the negative 1 of x equals x over 2, or you might have it as 1/2 x. That's its inverse. If I multiply, the inverse is to divide. Now I do have a problem with inverse operations because it doesn't always work and it sometimes leads us to the wrong answers. So I would prefer to find an inverse that we follow these 3 steps. To find an inverse, we're going to follow 3 steps. 1, we're going to switch x and y, just like we did by graphing. So the first step is to switch x and y. The second step is to solve for y. So once you switch x and y, you're always going to solve back for y. And then the third step is to write it in function notation. Write in function notation. So what am I talking about? I'm talking about putting it in to the idea of f to the negative 1 of x, or g to the negative 1 of x. So switch x and y. When you solve for y, you are going to use inverse operations and then put your answer in function notation. Now the last part of this problem is going to ask us to put the input in. So if we take 7 and we put it into the original function, that would be f of 7 equals 2 times 7. So f of 7 equals 14. Now take that answer of 14 and plug it into the inverse. F to the negative 1 of 14 is equal to our inverse, which was 14 divided by 2. And f to the negative 1 of 14 is 7. So what we're seeing is we put 7 in, and we put it into the inverse, and we got 7 back out. So the directions here tell you to use inverse operations. I would prefer that you use the 3 steps to finding an inverse to double check. So when doing these problems, we can use inverse operations, but we want to be really careful. So the inverse of division on a single step problem is multiplication. So my function is f to the negative 1, inverse notation, of x is equal to 3x. So if on a single operation, I'm comfortable using inverse operations. The inverse of addition is subtraction. So my inverse function is f to the negative 1 of x equals x minus 10. Where I'm not comfortable to use inverse operations on multi-step problems, because this is one of the mistakes that people make. So I'm using an extra piece of paper here. And the mistake people make is they look at this f of x and they say, okay, well, the inverse of division is multiplication. So here's my inverse, and they're going to do 4x, and they say, well, the inverse of addition or subtraction is addition. And the problem with this is that it is wrong. You would have to know that if I add on the 5, that is the inverse, but when I go to multiply the 4, I have to multiply everything by 4. So the answer would be 4 times the quantity, x plus 5. And I think that this is a common mistake. So I would like to return to our 3 steps. So again, when we have a 1-step problem, no problem, use inverse operations, but this method will always work. When you switch the x and y, solve for y, and write it in function notation. Now we have to be careful with our order of operations. So I'm going to set up for my inverse, but remember, this is the same as y. So I'm going to flip the x and the y. So it is going to be x equals y over 4 minus 5. And so when I start my inverse operations to solve this, I'm going to start by adding 5 to both sides. And so I get x plus 5 is equal to y over 4. And this is where it comes in. I get rid of division by multiplying, just like we said. But when I multiply by 4 over here, I catch that everything has to get multiplied by 4 using my rules. And so I would get, this cancels, y equals, in parentheses, 4 times the quantity x plus 5. And this is a perfectly acceptable answer. Put it in function notation, or you might distribute it and get 4x plus 20. So either answer in function notation is acceptable. So you could have it as 4 times the quantity x plus 5 or 4x plus 20. But if you end up with just 4x plus 5, then that is not its inverse. Okay, so we have here again a single step. So yes, the inverse of subtraction is addition. So we would get x plus 1/2. And just to show you, whenever we do this, if I went through my steps, switching x and y, again, I would switch and make it x equals y minus 1/2. And then the inverse operation of subtraction is to add 1/2. And that is where I would get y equals x plus 1/2. So we get the same outcome. And then we look at this, and we have, again, inverse, two operations that we have to invert. So I think it is in our best interest to replace the y and go ahead and step to taking x equals 3 times the quantity y minus 7. Now there's two ways to do this problem. I would divide by 3 to get that out of there. So I'm dividing by 3, and I have x over 3 equals y minus 7, and then I would simply add the 7. And that gives me x over 3 plus 7 is equal to y. And being x over 3, that is the same as 1x. We want to remember there's a 1 there, and so dividing by 3 is the same as saying 1/3. So here is my inverse function. F to negative 1 of x is equal to 1/3 x plus 7. Now, another way to do this, I prefer not to distribute the 3. I divided it out, but a lot of students will distribute the 3. So you'll have x equals 3y minus 21. And if I do that, I'm going to add the 21, so I get x plus 21 equals 3y. And then I'm going to come in and divide everything by 3. And so I'd have everything over here divided by 3. I prefer to break it up, and I end up with that same result of x over 3 plus 7 equal to y. The other acceptable answer would be f to the negative 1 of x is equal to x plus 21 all over 3. And if we take a minute and we look at that, there is the x over 3, 1/3 x, and there's the 21 over 3, which is 7. We're going to go over some examples of graphing inverse functions, and we're going to talk about linear graphs. And so we have our function f of x equals 3x plus 6. So we're going to go ahead and write and graph the inverse. So we're going to start by looking at f of x, remembering that f of x is the same thing as y equals. So we have y equals 3x plus 6. We're going to go back and revisit the idea of graphing a linear equation. So our slope is always paired with x, which is 3, or 3 over 1, and our y-intercept, our starting point, is 6. So we're going to go ahead and graph that starting point at 6 on the y-axis. We're going to rise 3, 1, 2, 3, run 1. I'm going to make a couple extra points. I'm going to drop 3 and go left 1, and drop 3, go left 1, because I want an accurate graph so I can show you where they cross when I find the inverse. So I'm going to draw in my line. There is my line. And the next thing we want to do is we want to find our inverse. So I'm going to remind you that when we find the inverse, the first step we talked about was switching the x and y. And so we are going to go with x equals 3y plus 6. And then the next thing we would do is we always want to solve for y. So in order to solve for y, I'm going to subtract 6. So x minus 6 is equal to 3y. And the next thing I need to do is get y by itself. So I'm going to divide each piece. I'm choosing to divide each piece rather than one big fraction, so I can look at it in slope-intercept form. So I have y equals, and there's a 1 here, so 1/3 x. X divided by 3 is the same as 1/3 of it, minus 2. And I want to put this back in function notation, so f to the negative 1 of x is equal to 1/3 x minus 2. And here I have my inverse function, and so I can see here is my original function f of x that I have in red, and here is its inverse. So I'm going to go ahead and graph this with a slope of 1/3 and a y-intercept of negative 2. And so when I put this on my graph, I start on the y-axis at negative 2, I rise 1, and I run 3. Go ahead and do a couple more points to make it accurate, and I'll sketch in my line. But what I want to talk about here is that line of reflection. These graphs reflect over the line y equals x, and that line is right here at 1, 1 and 2, 2, and so we have our line y equals x. That is where it's reflecting, reflects over y equals x. And so if I keep sketching this line, you can see if my inverse and its original function overlap, they overlap there on the line of reflection. And you can see that this point of 0, -2 reflects over here to -2, 0. And the point of 3, -1 reflects to a point of -1, 3. The x and y have inverted. All right, so we have another example like this, and I like this example because we have to deal with a fraction. First thing we're going to do is we're going to go ahead and graph the original function. So we'll set it equal to y equals, and that is 2/3 x plus 2. And again, I have a slope of 2/3 and a y-intercept of 2. So I plot my point at 2, rise 2, run 3. Go ahead and put a couple extra points on here. I'm going to reverse it and go down 2 and left 3. I still get a positive slope that way. Positive slope should always run uphill. All right, there's my graph. And then we're going to come in and we're going to switch x and y to find the inverse. So x is equal to 2/3 y plus 2. First thing I'm going to do is subtract 2. So I'll subtract the 2 from both sides, and I get x minus 2 is equal to 2/3 y. Now here's where I prefer not to divide. So I have 2/3 times y. I would definitely divide by 2/3 to cancel it. But we don't want to divide by a fraction if we don't have to. So what I'm going to do is I'm going to multiply by the reciprocal of 3/2 on both sides, by the reciprocal of 3/2. And so this is going to go ahead and cancel. It's 6 over 6, or the 3's cross cancel and the 2's cross cancel. And I'm going to go ahead and distribute that. So I end up with y equals 3/2 x. And then my 2's are going to cancel, and then just minus 3. So in function notation, f to the -1 of x is equal to 3/2 x minus 3. So I'm going to go ahead and graph my inverse with a slope of 3/2 and a y-intercept of -3. So we're going to plot that point. We're going to rise 1, 2, 3, run 2. Same thing, rise 1, 2, 3, run 2. Rise 1, 2, 3, run 2, and I found their intersection, which we're not really looking for, but again, I want to point out that their intersection is right on that line of y equals x. And so we can see, if we could take our folder or our paper and fold it over, we would see the reflection of these points. All right, we have a couple of word problem examples here, and we can do these in a couple different ways. So let's go ahead and read through this one. A clerk needs a price on a digital camera returned by a customer, and the customer paid a total of $103.14. That included gift wrapping and an extra charge of $3. Gift wrap for an extra charge of $3 and an 8% sales tax. So what price should the clerk mark on the tag? So this was the total cost, and that included gift wrapping and sales price. So the total charge, or the total cost, would be equal to 1.08 times the price of the camera plus 3. All right, so C stands for the total cost, including tax and the gift wrapping fee. And P stands for the original price of the camera. So we have to think backwards here. So if I'm looking at this, the P plus 3 is I have a price of the camera plus $3 to gift wrap. And the 1.08 comes from the tax. You're going to pay for 100% of this camera plus 8% tax. That gives us a grand total of 108%, which is a decimal 1.08. Multiply by 1, I get the cost back, and then another 8% added on. So it says find the inverse function that models the price as a function of cost. So we're going to go ahead and reverse this. And so if I wanted to, I could take this $103.14 and plug it in and solve for P. So we could solve it that way. But since we're practicing using our inverses, we're going to go ahead and do that. So again, I could take my 103.14, plug it in, solve for P by dividing by 1.08, subtracting 3, using inverse operations. We want to find the inverse function. Now, the rules to finding the inverse function were to switch x and y. However, x and y had no meaning, but C stands for the total cost and P stands for the price. So when we find the inverse function, we are going to solve for P using inverse operations. So we're going to solve for P using inverse operations. So we want the inverse to be a model of the price. Right now, it's the price gives us the cost. We want to find the price based on the cost. So I'm going to go ahead and start by distributing by that 1.08. You might not distribute. Maybe you keep it and you work backwards on that. And if I do that, the next thing I'm going to do is subtract the 3.24. And to get P by itself, I'm going to divide both sides by 1.08. Divide. I'm going to go ahead and show this. It's not proper to leave a decimal within a fraction. So I need to remember to divide this out. And this is one of the common mistakes made. So a lot of people end up writing that this is 1.08c and it's not. I actually need to take 1 and divide that by 1.08. And I find out, and this is a decimal, so I'm definitely rounding, and it's going to be about 0.926c. And then I'm going to take that negative 3.24 divided by 1.08, and I get a nice minus 3 here, and that equals P. So the price of the camera is equal to 0.926 times the total cost minus the $3 wrap. All right, so evaluate the inverse function for this. We are going to take our cost and put it in for C. So the price is equal to 0.926 times the cost of $103.14, and then take away 3. Now remember, we did round that 0.926. We did round that. All right. Calculator's a little blurry, but we'll work with it. So 0.926 times 103.14, and then I'm going to subtract 3. And we get a grand total of $92.51. So the camera cost should be $92, and I'm going to go ahead and round that to 51 cents. Depending on how you rounded this number, you might have just gotten it as an even $92.50. That is the price of the camera tag, not including tax.